Hello students, welcome to physics bouquet. In this video, we will discuss about Rayleigh's law of heat radiation. This Rayleigh's law, it gives idea about spectral distribution of energy. A spectral distribution of energy radiated by a black body which is in thermal equilibrium. In the form of spectrum, how the electromagnetic energy of radiation of a black body is distributed, that is given by Rayleigh's law, and it is based on two assumptions. First assumption is the electromagnetic energy radiated by black body is in the form of, it consists of standing waves, which are also called stationary waves. So the energy radiated by the black body, that is electromagnetic radiation, consists of stationary waves or standing waves, and that are considered as oscillators or also called resonators. Resonators or oscillators. This is first assumption, and second assumption is energy is continuous. Energy is continuous. It is not discrete. It is continuous, and at thermal equilibrium, each independent mode of vibration, each independent mode of oscillation has average energy equal to kT. And remember, this is a classical approach to deal with spectral distribution of energy. That means it is being explained classically. Quantum mechanical explanation is not given here. Rayleigh's gave classical explanation. So energy distributed is continuous, and for each mode of vibration the average energy is equal to kT. It is from equipartition theorem. So these are two assumptions. And mode of oscillation, I want to recall that mode of oscillation means it is a pattern of oscillation dependent on frequency. For example, suppose a string is being plucked. Suppose it vibrated so that a standing wave is formed. These two are called nodes and these are called antinodes. So see, this is half of a wave. That means this is lambda by 2. This is one mode of oscillation. Then it can be like this also. This is fundamental mode of oscillation. Then another mode, it can also be like this. So these are different modes of oscillations. So for each mode of oscillation, the average energy is kT. Range. Suppose the frequency range is nu to nu plus d nu. Within this frequency range, the energy density, energy per unit volume, the energy density u nu d nu will be equal to the average energy of each mode of oscillation, average energy of each mode of oscillation or each mode of vibration into number of modes of vibration, number of modes of vibration within the range nu to nu plus d nu. Suppose this is equation number 1. Of course, we have taken E is equal to kT. Let it be equation 1 and it be equation 2. This average energy is given in this assumption. We have to find out the number of modes of vibration within the energy within the frequency range nu to nu plus d nu. That we have to calculate. To calculate the number of modes of vibration, let us consider that the radiation be enclosed in a cubical box the energy is enclosed within this cubical box, and each side of the cubical box is suppose A, and the walls are reflecting in nature. Walls are perfectly reflecting. Let me write perfectly reflecting to maintain the temperature. That means temperature to be kept fixed. Walls are made perfectly reflecting, and the enclosure is hollow cubic box. Enclosure is a hollow cube whose walls are perfectly reflective. When the electromagnetic waves within this, the radiant energy enclosed in the hollow cubic box, the electromagnetic waves, they travel in all possible directions and get reflected from the walls of the enclosure. When they get reflected, undergo multiple reflections, those reflected waves interfere with each other, and due to that interference, standing waves or stationary waves are formed. Understood? Suppose a wave is traveling along this direction. Suppose this is O, it is traveling along this direction. With x-axis, suppose this is x-axis, y-axis, and this is z-axis. Imagine this angle is suppose alpha, this is beta, and this one is gamma. So alpha, beta, gamma, these are direction cosines. along which the electromagnetic wave, particular electromagnetic waves travel. We have taken this to be A, this is A, and this is also A, each side is A. Then the projections of different edges For example, this is x-axis. If we draw a projection matlab what? Suppose this is angle theta. If we draw a projection on this, on the x-axis, if we draw a normal or perpendicular on the x-axis, then this is the projection of this. Suppose this is OAB. So OB is the projection on x-axis of OA. OB is the projection of OA on the OX. Right? Similarly, if we draw projections from different edges, from x-axis, y-axis, z-axis on this direction, then we will get A alpha, A beta and A gamma. These are projections of different edges. Now you will find out the allowed wavelengths. Before going to allowed wavelengths, let me go to the modes of oscillation. Suppose this is length L and the fundamental mode of vibration is this. That means it is half of the wavelength. That means next part is like this. So this is half of the wavelength. Then L is equal to our lambda by 2. Then lambda is equal to 2L. Then another mode of oscillation. This is another mode of oscillation. Here this length is L. This is lambda by 2. This is lambda by 2. So total is lambda. So lambda is equal to L. I can write it as lambda is equal to 2L by 2. This lambda is equal to 2L can be written as 2L by 1. Like this. Third mode of oscillation. Lambda by 2, lambda by 2, lambda by 2. 3 lambda by 2. So here L is equal to 3 lambda by 2. And it can be written as lambda is equal to 2L by 3. So you see, like this, if we take different modes of oscillation, we will get 2L by 1, 2L by 2, 2L by 3, 2L by 4, 2L by 5 like this. So these are allowed wavelengths. So in general we can write lambda is equal to 2L by n. Lambda is equal to 2L by n, where n is a positive integer. Now come to our discussion. Here the allowed wavelengths can be written as lambda is equal to, for x-axis projection we can write lambda is equal to 2A alpha by suppose n1, 2L by n1, L के जगह A alpha, and n1 is a positive integer. So for y-axis allowed wavelength is 2A beta by say n2, and for z-axis we can write 2a gamma by n3. n1, n2, n3 are positive integers. Now from trigonometry we know that our sum of squares of directions cosines alpha square plus beta square plus gamma square is equal to 1. This is a relation from trigonometry where alpha, beta, gamma are the direction cosines. Now if we isolate alpha from here, then alpha is equal to n1 lambda by 2a, n1 lambda by 2a इसका square. Similarly beta is n2 lambda by 2a का square, and gamma is equal to n3 lambda by 2a is equal to 1, right? If we take common lambda square by 4a square within the bracket is equal to 1, or n1 square plus n2 square plus n3 square is equal to 4a square by lambda square. But we know that there is a relation c is equal to nu lambda, then lambda is equal to c by nu. So using c by nu in place of lambda, we will get 4a square nu square by c square, or we can write n1 square plus n2 square plus n3 square is equal to 2a nu by c whole square. Let it be relation 3. So for a particular frequency we have different values of n1, n2, n3. That means there are different sets of values of n1, n2, n3 for a particular frequency. That means for a given frequency we can have different sets of values of n1, n2, n3, and those sets of values of n1, n2, n3 are different modes of vibration. For a given frequency we can have different modes of vibration. So it is little bit lengthy to find. It is a lengthy derivation to find out the modes of vibration within the range nu and nu plus d nu. So I have divided it into two videos. In this video let me stop here, and in next video I will find out I will complete the topic with calculation of total number of modes of vibration and the Rayleigh jeans. Have a good day.